Hi Planet Earth, this video is meant to provide you an introduction to topographic and geologic mapping, which are two skills that we're going to be using quite a bit in this course. First, let's talk about topographic maps. I found a really good video from REI that will introduce you to this. This is probably some content that you've seen before, most likely in middle school in like an earth science class, but this will provide a good review.
Topographic maps are a little different from your average map. Not only do they show the location of things like roads and trails, but once you get the hang of reading them, they also help you visualize three-dimensional terrain from a flat piece of paper. Topo maps use three main mechanisms to describe the terrain. In this video, we're going to cover how to read the map's contour lines, how to understand scale, and how to read the symbols and colors found in the map's legend. Contour lines are what really make topographic maps something special. These lines connect all the points on the map that share the same elevation. By looking at how the contour lines spread out and come together, you can get a good sense of what the terrain looks like. When the lines are packed close together, that tells you that the elevation is changing a lot in a short distance, so the terrain is quite steep. As the lines spread out, the elevation changes more slowly, so the slope is more mellow. Contour lines can also help you visualize the shape of the terrain. For example, as the lines form smaller and smaller circles, they're probably showing a peak. Spend some time with a map of a familiar area and see if you can pick out terrain features just by looking at the contour lines. Every fifth contour line on a topo map is thicker than the others, and those thick lines are called index lines. At some point along every index line, you'll find the elevation for that line written on the map. The change in elevation from one contour line to the next is always the same on the map. And most maps have either a 40 or 80-foot contour interval. If your map has an 80-foot interval, that means that each contour line is 80 vertical feet away from the next. You can find all the specific details about the contour intervals and index lines for your map in its legend. Scale refers to the relative distance of the map. For instance, this map scale is 1 to 12,000. That means that 1 inch on the map represents 12,000 inches in reality. Another map of the same region is 1 to 50,000 and covers a larger area, but in less detail. The important thing is that the map with a smaller scale will show a smaller area, but with more detail. Understanding the level of detail on your map is handy when planning your route, but it isn't much help if you want to calculate distances efficiently. That's why maps also have a small representative scale near their legend. This scale shows you the relative distance of a mile or a kilometer on your map, and you can use the edge of a compass or even a piece of string to help figure out just how far away that peak is. One of the first things to look for on any new map is the legend. The legend is like the user's guide for your map. It's where the various lines, colors, and symbols are defined. When it comes to the colors on the map, the idea is that the darker the color, the denser the vegetation. As you get closer to the top of a peak, you'll notice that the colors get lighter as the forest thins out. And of course, streams and lakes are represented in blue. Alongside the list of symbols, there are a few other important pieces of information, like details about the contour lines and the date of the map's most recent revision. This is also where you'll find the magnetic declination for the region, which you'll use to set up your compass. When you combine your understanding of contour lines, scale, and your map's symbols and colors, you can almost visualize your whole trip before you go.
Okay, so that provided a good general introduction. Just to review, we have this concept of the contour line. And contour lines are lines on topographic maps, and they critically connect points of equal elevation. As they mentioned in the video, sometimes you'll see contour lines that are darker at intervals, and these are usually the ones that are labeled, and they're called index contour lines. So you can get an idea of the elevation of each index contour line because it's normally labeled on the map. Based on the map's contour interval, you can then figure out the elevations of all of the contour lines. And then there's this term contour interval, which we'll talk about in a little bit in more detail, but that's the elevation change between contour lines. Now, one important thing that I've noted down here is that a rule for contour lines is that they cannot cross. And this is just a rule for topographic maps. You can probably imagine a sort of a geologic scenario, a topographic scenario where contour lines might want to cross. let's say you're in like Arches National Park or something and you encounter a feature on the terrain that looks like this. And we're looking at this from the side, of course, and I've put some stick figures on there to show you kind of the perspective. But note, let's look at this point, for instance, right here. Well, that point has a specific elevation, but if you're looking at it from top down, you'll notice that there are other elevations at that exact same point. So what would that look like theoretically on a topographic map? Well, you might want your topographic lines to cross in this instance because you have multiple points of elevation at the same point when you're looking at it from the sky. But what the topographic map would illustrate for this is something like that. So it would just look like, from a topographic map perspective, like you have a very steep drop in that region. So this area here that I've labeled in red on my sort of cross-sectional diagram at the top would really be invisible on the topographic map. So these maps are not giving you every aspect of terrain, but they're definitely giving you a lot of useful information about the landscape. So a review of important terms to know regarding topographic mapping. First, scale. So we have ratio scale, which we've talked about before in the context of that aerial photos activity at the beginning of the course. But the video introduced bar scale. And what the bar scale is giving you is just something to measure with either a ruler or a piece of paper. And if you measure that length, that gives you the corresponding distance in real life of that length on the map. So you'd take a piece of paper, hold it up to this, put one end right here, one end right here, and that length would be on your map 400 feet. One thing that I want to make sure that you are aware of that is tricky sometimes is sometimes you get bar scales that look like this. And I always want you to pay attention to where the 0 is, because a lot of times people will go to the task of measuring this entire thing here and saying, okay, that's 200 feet in real life. That's the value of 200 feet in real life on the map. You need to start at the 0. So you can see in this one over here on the left, my 0 is there, and the scale just goes this way. Sometimes they'll give you the 0 in the middle with a scale going both ways just to give you different breakdowns of that scale. So make sure that if you're presented with a bar scale that looks like this, you only measure that amount as being 200 feet in real life. And then lastly, the simplest one is the verbal scale. A lot of maps will have this, which is just a statement saying, okay, this many inches on the map equals this many feet in the real world. Very easy to interpret. Another mapping term that is important to know is distance as the crow flies. And I don't know the origins of this term, but you can imagine if you had a bird that was flying in a most perfect way, the shortest possible distance between 2 points, right? So we're talking about straight line distance here. So if you're asked to measure distance as the crow flies between 2 points, just draw a straight line between them, measure that distance. Here's a formal definition of contour interval. As the video reviewed, this is the elevation change that occurs between each contour line on a particular map. On a test, if you get this question, define contour interval, please do not write the distance between contour lines. I hope you can see why that's incorrect. You're not measuring, it's not the distance between contour lines as the crow flies, for instance. What we're talking about is the elevation change between contour lines. Relief is another term that you need to know. Relief is a term for mapping that basically describes total change in elevation. So if I asked you to calculate the topographic relief in a given grid cell on a map, you would find the highest elevation, you would then find the lowest elevation in that grid cell, and you would take the difference between them. If I asked you to calculate the topographic relief between 2 points, you would find the elevation of point A, the elevation of point B, take the difference in elevation between them, and that's the relief. And then lastly, gradient, or topographic gradient. This is the mapping equivalent of slope, rise over run. So given terms that we've defined on this page, if I asked you to calculate the gradient between 2 points on a map, you would first find the topographic relief between those 2 points, the difference in elevation between those 2 points. And then you would calculate the distance as the crow flies between those 2 points, and then divide them. So relief between those 2 points, divided by distance between the 2 points as the crow flies. Rise over run. So here's a task, and I've given you a very zoomed in topographic map where this is easier. A lot of times, as illustrated in that video, your contour interval is going to be given to you at the bottom of the map, so always check for that first. But if I gave you a tricky test question where I gave you a map where the contour interval wasn't explicitly listed at the bottom of the map, you can figure it out. So pause this, take a second, see if you can determine what the contour interval is on this zoomed in topographic map section. Elevations are in feet. Okay, hopefully you've paused it and gotten an answer. Let's review. So first thing you're going to want to do is obviously look at the data you're given. We're given 2 index lines here, a 700-foot index line and an 800-foot index line. So the elevation change between those index lines is 100 feet. Now all you need to do is figure out how many contour intervals exist between those index lines. Here's 1 contour interval, 2 contour interval, 3, 4, 5. So you take your elevation change between index lines of 100 feet, divide that by the number of intervals between, which is 5, and you get a contour interval of 20 feet. Hopefully that makes sense. Here's a much more elaborate explanation of how to do that. One thing that I find is the most common error here is people take this elevation change between index lines of 100 feet and they divide that by the number of lines between those index lines. 1, 2, 3, 4. And if you did that, you'd get 25 feet. Now, that is notably the wrong answer. So make sure you're dividing it not by the number of lines, but notably by the number of actual contour intervals, not 4, but 5. So let's move on to geologic maps. Geologic maps are, I think, in my opinion, a lot more interesting to look at. They're a lot more colorful than topographic maps, and they provide you with a completely different allotment of information. So what you're looking at when you're looking at a geologic map is you're looking at the rock type or soil type on the surface of the Earth in the area represented by the map. So this is a geologic map of Yosemite National Park, and you can see that Yosemite National Park has a wide variety of geologic features. These are symbolized in different colors. Now, I don't want you to associate these colors with the actual colors of the rock types. These rocks are definitely not these colors. These colors just exist because a lot of these rocks look very similar in color, so they want to be distinguished. So what lines are on a geologic map are what are called contacts. And you can see down here that that's in the key. So what a contact is an interface or a line separating 2 geologic formations. So like for instance right there, we're separating this geologic formation from this one. All your information about what geologic formations these are is contained in this thing on the right, which is a key. It's technically called, for a geologic map, an explanation. One thing you need to know about an explanation on a geologic map is as you go higher, you are getting younger and younger in terms of the age of the rock. So younger stuff is at the top, older stuff is at the bottom. And you can see that by looking at these time periods: Paleozoic, Mesozoic, Triassic, Cretaceous, Jurassic, Cretaceous, later Cretaceous, Tertiary, Quaternary. So that's important to know. And a geologic map will also have a lot of other information on it. You can see here that geologic maps will also show faults. And so some examples of faults on this map would be like, okay, like right here, there's a fault and you see those little things on the side indicating that it's a fault. And what a fault is a fracture or zone of fractures between 2 blocks of rock. So as this course, we're comparing physical and biological characteristics throughout geologic time. You'll be using geologic maps quite a bit to assess what's physically present in an area. So we're going to get you to practice these skills through an introductory activity that's going to have you evaluating topographic and geologic maps of Austin. Here's a screenshot of the topographic map you're going to be analyzing. This is West Central Austin. Some spots you might be familiar with. This road here is Mopac, and you can see it crossing Town Lake or Ladybird Lake there, down at the bottom. This general area is Westlake Hills. Some of you might have visited Mount Bunnell in your life. It's definitely a great spot to visit. It's right there. And down here we have Redbud Island, and so you might have visited the Hula Hut or the Mozarts there, and crossed this bridge next to this dam, the Tom Miller Dam. There's the bridge. And this whole neighborhood over here is Tarrytown, so you can get an idea of where this is in Austin, at least. This is the map you're going to be evaluating, and you're going to be answering some questions that are going to ask you, yes, to calculate some things and practice analyzing topographic maps, but also will hopefully give you an idea of what Austin looks like topographically, which will in turn lead to the geology part. So the second part of this will be analyzing a geologic map of Austin. And there are a lot of colors here, and you can see a lot of things going on. So this is very fortunate for our course. It's fortunate we're teaching a course that has a geology component in Austin, because its geology and geologic history are really ornate. So it's going to ask you, the second part of this activity is going to have you evaluate geologic features in Austin. And you'll note that the topography really connects with the geology. And this is going to bring up a lot of really interesting aspects of Austin's geologic history that'll definitely help us out in the future in this course. A couple things about reading geologic maps, especially this one we're going to be looking at for Austin. So when you see these symbols like this, like QAL, what the Q stands for is the time period. So this Q is standing for Quaternary. The AL is an abbreviation for alluvium, which is the rock type. Down here, you can see we have KGT. The K stands for Cretaceous. And why they don't use C, well, there is already a C prior in geologic history from, obviously, the Cambrian. So they had to pick a different letter. K is representing the German word Kreide. That's an awful pronunciation, which is spelled Kreide, and that word in German means chalk. And if you've been in Austin for at least a little bit, you know that a lot of this Cretaceous rock is limestone, chalk rock. So long-winded, but that's where that comes from. So that provides you at least an introduction to this Austin topographic and geologic mapping activity.